Alright guys, another day of linear algebra. I can say I kind of was excited for this. So we've been talking about recently, we've been reading this proof appendix. What is proof? Right, a proof is basically a logical argument that shows the validity or aims to show the validity of a conclusion based on logical steps. So each logical step must reference basically a truth that's self-evident, or an axiom that's self-evident, or something that's been previously proven. Okay, proofs are often formality. So in some math courses, proof formality is pretty important, but in linear algebra, the formality isn't super important. It can be in English. It can be written in sentences. Proofs can be also often written in symbolic form, and a symbolic form of a proof in the simplest way possible. Simplest form is basically hypothesis, or like a symbol, like a H arrow C, hypothesis arrow to conclusion. So the beginning is the hypothesis, is it basically if, the arrow is then, and then the conclusion, stating that if the hypothesis is true, then the conclusion is true. So in order for this to be a true statement, every time the hypothesis is true, the conclusion must be true. If the hypothesis is ever true and the conclusion is false, the statement is forever false. Okay? We can also see, so then we talked about the contrapositive. So the contrapositive of a statement is basically you take the order of the hypothesis and conclusion and flip them, and also make them both negative. So this little squiggly line is like the opposite. It's like a not, or it's like a false if the thing is true. So basically contrapositive is you're switching them and you're negating both. So saying if not C, then not H. So the contrapositive will also always be true if you have a true statement. The converse, however, is not always true. It can be true or false. The converse of a statement is basically you're flipping the order of the hypothesis and conclusion, but you're not negating them. Okay. If, however, the converse is also true, well, then you have some statement that's like, is it equality? Something about equality. I don't remember. There's some term for equality statements, equal statements, equality of statements, when the converse is also true. Symbolically, when the converse is also true, you can write it with a double arrow, so an H, or H double arrow C, and that can be read as H is equivalent to C. They're equivalent statements, that's what it is. H is equivalent to C. That's the double, or also can be read as H if and only if C. So that double arrow can mean is equivalent to, or it can mean if and only if, same thing. So these are equivalent statements. Then we're talking about basically, I think it was the transitive property, but it didn't mention transitive property, but it basically saying we can get a free proof or truth if we have two statements where in which one conclusion is the same as the hypothesis of another. So if A, then B, if B, then C, you can get a free proof out of that by saying if A, then C. Anything I'm missing? Okay, another way to write that if and only if statement is if hypothesis, then blank and blank. So and. Okay. Cool. So I'm going to finish reading up this section on how to read theorems. and then go back to recall the last of it. Maybe I'll read the next section as well. All right, I'll be back in a sec. All right, so the end of that section on how to read proofs was kind of like a more extreme version of the transitive property, if that's what it really is. Anyway, where we could get one free proof if we had two, that I just stated before. Well, there's the next step is like, if you have three statements in what they call an implication loop, you can get three more proofs for free. And that is, if A then B, and if B then C, and if C then A. Then it's like a loop. And then you can say, if A then C, if B then A, and then if C then B. Yeah. I think that's right. So implication loop, and then the next section was called reductio ad absurdum. Reductio. All right, that was a quite unfortunate event. My phone happened just to die, but we're back. Reductio ad absurdum. This is a concept in logic in which a statement cannot be true and false. Cannot be both true and false. It just cannot be. It's against logic. And so one way of trying to prove or disprove something is to show that, it's both true and false, which will make the statement false. So the example given is the hypothesis essentially in the form of H and not C, then C. Okay? Interesting. We'll continue now. Continue reading on into the section now on sets. Doesn't look huge. Sets, I believe, these are just groupings of things. So we'll find out. I'll be back in a sec. All right, there was a lot in there. That was the section on sets. They kind of assumed that we knew what sets are, and how they work to the basic levels. I really haven't studied sets much, just a tiny bit in a liberal arts math class. So what is a set? Set is really simple. It's really simply just a collection of objects. And the objects within a set are known as elements. Okay, that's the basics. The notation is typically, the grammar of it is typically like capital letters indicate sets themselves, lowercase letters indicate elements. Lowercase letters indicate elements. Okay. Okay. There's some ways to denote infinite sets. If, for example, if the numbers follow a logical numerical sequence, then you can add ... to the end after the pattern is obvious. So such as 1, 2, 3, 1, 2, 3, ... indicates it's going to keep going for infinity. That's an infinite set. Another infinite way to denote an infinite set for all these, what would these be, whole numbers or positive integers is another way to say it, I guess. You could say, you could put it in set builder notation, which generally follows the form within the braces is x colon blank, where the blank is a definition, and x colon is read as the set of whatever, say it's R. The set of R is such that, what is it actually? The set of all x. Oh, okay, the set of all x. So x semicolon is the set of all x such that, definition. X is a positive integer. X is a positive integer. Is that how you write it? Yeah, you can write it just x is a positive integer, exactly like that. And then there's a symbol in sets, which I've seen before, and I never really knew what it meant, but now it's super simple. It looks like an E, but like it's like a C with a horizontal line going in it. Looks like an E, but made of a C instead of like a rectangle. It's like a semicircle, and that is it just means belongs to. So you say element belongs to the set, or you can say does not belong to by putting a cross through that belongs to symbol. Okay. Some sets that are of particular importance in linear algebra are real numbers. So R, points in a plane, and this is R squared, and then points in a three-dimensional space, which is R cubed. Anything I forgot there? Order of elements does not matter within a set, and there cannot be any elements that repeat. Right, and the elements in linear algebra are typically scalars, matrices, or vectors. Okay, that's that. We got a few more minutes. There's the next section is called operations on sets, and that's what I'll read and be back in a second. All right, guys, wrapping up today. Just read a lot more about sets, operations on sets. And I have learned this stuff. Maybe not all of it, but I have learned this stuff. I'm happy I took that. I'm so happy I ended up taking that math class in community college. And it was the lowest level math class, 6 credits, enormous scope. Got a little bit of slices of everything. And I'm very happy I took that class because I wanted to get a foundation in math. And I did. And I would have never learned about the sets and stuff otherwise, except this would be all brand new to me. So it was a great ending, great choice in the end. Now let's get back to this. Right, I just learned like 6 different terms. So when we're talking about sets, they call them arbitrary sets. I think that my understanding is it looks like those are arbitrary sets or finite sets, meaning they're not infinite sets. So when you've got Venn diagrams that represent these sets, when there's overlap, if you consider there's a symbol called U as a union, it looks like a U kind of, that means when these Venn diagrams, you're talking about everything. You're talking about the one in A, stuff in B, and they overlap. That's a union. An intersection is just the stuff that intersects. It's in the middle. It's shared by both sets. That's denoted by basically the union symbol flipped upside down. That's called an intersection. When these sets don't overlap at all, there's no overlapping elements, well then basically you have an arbitrary set. And the intersection is an arbitrary set, meaning there's no overlapping things to intersect, no overlapping elements. And that is denoted by basically a 0 or an O with a line through it. That's denoting an empty set. So union, intersection, empty set. Arbitrary set is when you have the union at the intersection, but there's no overlapping elements. Then we talked about subsets. So if all of one set is within another set, then you say this set is a subset of this set, like they're all within this. And if both are subsets of each other equally, that means they're equal sets. Subset, there's a symbol, it's basically the intersection or union symbol but flipped on its side. Looks like kind of like a C. Oh wait, it was not an arbitrary set. It was a disjoint set. Intersection is an empty set is what a disjoint set is. Okay, learned a lot about sets today. What else did we do? We finished up on proofs. Yeah, we talked about, okay, yeah. Implication loop, sets, reductio ad absurdum. Okay. Actually, yeah, holy cow. All right, we got less than half a page left in this Appendix A, working with proofs. So we're going to be done with this maybe tomorrow. Nice. And then we'll go into complex numbers, Appendix B. So this is imaginary numbers, or complex numbers, actually, but okay, this will be good to go through. Oh, this is way longer than the working with proofs. So working with proofs was 4 pages. This is 1, 2, 3, 4, 5, 6, 7. Okay. So not double, but it's definitely longer. Yep. That's where we're heading. Talk to you guys later.